To watch these important lessons, subscribe to DP Education's YouTube channel right now. Click on the bell icon to stay updated on the latest lessons. Sri Lanka's largest free online school, DP Education.
Hello my dear students, welcome to today's lesson. So today also I am going to continue with the lesson electronics. Now in the previous chapter we did an activity to understand the biasing process of a PN junction. So there you were able to understand that there are two methods of biasing. One is known as the forward biasing, that is when current flows through the PN junction. So there the P region of the junction is connected to the positive terminal of the power supply. But in reverse biasing, the P region of the PN junction is connected to the negative terminal of the battery and the N region is connected to the positive terminal of the battery. And there is no current flow through the PN junction. I explained why that happens also, and I told you all again when I start this chapter, I will discuss that process again. So here we start this chapter by discussing reverse biased PN junction. So when we say reverse biased PN junction, here you can see. Let us consider what happens when a battery is connected to the junction with its negative terminal connected to the P-type semiconductor and its positive terminal connected to the N-type semiconductor. So, negative terminal is connected to the P-type semiconductor and its positive terminal connected to the N-type semiconductor. So, this is what I explained to you all. Now here you can see before biasing. The first diagram shows what happens before biasing. So here you have the P region and the N region, or the P type and the N type. That is how we get the PN junction. So you all can remember, students, the electron diffuse from there to here, holes diffuse from here to there. So because of that, there is a region that is devoid of charges. There are no charges. So that region becomes a potential barrier here, you can see. And that is what we call as the depletion region or the depletion area. So there what happens is, you can see this is like a hypothetical battery where the P region is connected to the negative potential and the N region is connected to the positive potential. So that is why it is a potential barrier. The depletion layer or the depletion region is a potential barrier. Then, if we connect the external power supply or potential difference is supplied to the PN junction, and that also reverse biased PN junction. Now here you can see after biasing, now there you can see, students, this is the negative terminal and that is the positive terminal. Negative is connected to the P side and the positive is connected to the N-type semiconductor. So what will happen? The bulb will not light. Bulb will not light. Why? Because current will not flow through the PN junction. What is the reason? When you connect the negative terminal here, there are electrons. The electrons come and fill up the holes. Because of that, the depletion layer moves towards this side. At the same time, the electrons here are attracted towards the positive terminal. So, they move towards this side, towards the positive terminal. Because of that, there is a broadened depletion layer. The depletion layer becomes broad. So, because of that, the potential barrier increases and that prevents the flow of current across the PN junction, and that is what we call as reverse biased PN junction. That does not allow current to flow through it. Therefore, the bulb does not light. You saw that during the activity. So, I am sure you all can understand what happens when we reverse bias a PN junction. Reverse biasing of a PN junction. With that, I'll move on to the next slide. So here, the explanation is given to you. In this case, the free electrons in the N region are attracted towards the positive potential, while the holes are attracted towards the negative potential, broadening the depletion layer. So, what I explained to you all before. So, here the free electrons in the negative N region are attracted towards the positive potential, while the holes are attracted towards the negative potential, broadening the depletion layer. So, that happens there. Then there is no carrier or charge flow across the junction. So, there is no carrier flow across the junction. Only the depletion region broadens depending on the potential difference of the external source. So, if you supply a higher potential difference, the depletion layer will broaden furthermore. So, depending on the potential difference, the broadness of the depletion layer will vary. But anyway, there will be no current flow through the PN junction. That is important. So, there is no charge or carrier flow across the junction. Since there is no charge flow, connecting the external potential in this manner is known as reverse bias. So, figure A and B shows how the depletion layer behaves when it is reverse biased. Is that clear to you all? So, we have already seen the figure A and B. So, in this, we saw figure A and B, before biasing and after biasing. So, I am sure you all can understand that, students. So, since there is no charge flow, connecting the external potential in this manner is known as reverse bias. Is that clear? So, reverse bias PN junction does not allow current to flow across it. So, with that, I'll move on to the next slide. So, here forward biased PN junction. That is the second method of connecting the PN junction. That also I explained to you all. So, here if we look at the first two diagrams, you can see now before biased what happens, you have the P region, N region, and this is the depletion layer. This region is the depletion layer. Why? Because the holes diffuse to this side, electron diffuse from there to here, and then what happens? There is a region devoid of charges. That becomes the potential barrier, that is the depletion layer. That is similar to a hypothetical battery like that, where the P region is connected to the negative potential and the N region is connected to the positive potential. So, that is before biasing. After biasing, what happens here? Now, the second one, very small current flow, that is when VB1. When we say VB1, that is the bias potential. Now, here this is the potential that we are applying to overcome the bias of the PN junction. That is the depletion layer of the PN junction. For that, we supply a potential during biasing. So, what happens there? We supply a current smaller than 0.7 volts. You all know for a silicon PN junction, if it is silicon PN junction, the potential barrier is 0.7 volts. So, we supply a voltage less than that. So, although there is a potential difference, now you can see compared to this one, this depletion layer is narrow. Why? We have the positive terminal here connected to the positive terminal, negative terminal connected to the negative terminal. So, electrons will move this way and they will try to push the electron towards the depletion layer. At the same time, holes start moving towards this side. Again, they will push the depletion layer towards the center. So, because of that, you can see the depletion layer has become narrower. It has become smaller. But still, it has not been overcome. Why? Because the potential that is supplied is less than 0.7 volts. So that is not enough for a current to flow across the PN junction. It is forward biasing, but still the current does not flow. Then what should we do? We need to increase the applied potential difference. So that is what we do here in this diagram. Now here a forward biasing of a PN junction, that is after biased. Here you can see the potential that is supplied is greater than 0.7 volts. Then what happens? Again, due to this positive potential, the positive terminal, holes are pushed towards the negative region. The same way, because the negative terminal is connected there, due to the electron flow, electrons are pushed from the N region to the P region. So what will happen? The depletion layer becomes narrower and narrower until there is no depletion layer. There is no depletion layer. So at that point, current starts to flow across the PN junction. And you all know the direction, students. How do they flow? Now electron flows this way. Electron flow. Whereas the holes flow this way. And the current also flows in that direction. So electrons flow from negative to positive through the PN junction. Holes flow from positive to negative, P to N, and the current also flows from P to N. That is after forward biasing a PN junction. A considerably large current flows. That is after biased. The biased voltage is greater than 0.7 volts. So the voltage that we supply from the external power supply is known as the bias voltage. It has to be greater than 0.7 if it is a silicon PN junction. Then only the PN junction will be forward biased. Is that clear to you all? So this is something that you all need to understand, students. So with that, I will move on to the next slide. In this case, the external potential source is connected with the positive potential connected to the P region and the negative potential connected to the N region. Very important. That is the process of forward biasing. So what do we do? The external potential source is connected with the positive potential connected to the P region and the negative potential connected to the N region. So the proper way where forward biasing can occur. While the holes in the P region are repelled by the positive potential towards the junction, electrons in the N region are repelled by the negative potential towards the junction. So this is also something I explained to you all. Holes in the P region are repelled by the positive potential towards the junction. Electrons in the N region are repelled by the negative potential towards the junction. That is also important. I explained this in the diagram in the previous chapter also. I showed you all how the electrons and the holes move. Then, here you can see the depletion region narrows down due to this. And if the externally supplied potential difference exceeds the potential barrier across the junction, carriers flow across the junction. You have to remember this also. Externally supplied potential difference exceeds the potential barrier across the junction, carriers flow across the junction. When a high potential then 0.7 volt is applied, depletion layer is very small and a current is flowing through the PN junction. Then a current flows across the junction. Therefore, Connecting the external voltage in this manner is known as forward biasing. Is that clear? So, when you supply a potential greater than 0.7, it is forward biased and the current flows across the PN junction. So, I am sure students you all can understand what forward biasing and reverse biasing are. So, with that, I am going to move on to the next slide. So, here we look at the electronic device that is made using the PN junction. We have already used this PN junction diode when we wanted to do the activity of biasing the PN junction. We used a PN junction diode. So, now we will try to understand what this PN junction diode is. Now, you know that a current flows across the PN junction only if it is forward biased in the manner described above. A component consisting only of such a PN junction is known as a junction diode. So, this is something you need to know. So, know that a current flows across a PN junction only if it is forward biased. And that component is known as a junction diode or a PN junction diode. The arrangement of P and N semiconductors inside a junction diode is illustrated in figure A. So, I will draw that for you all. So, first we will look at figure A. So, figure A, this is what is. So, this is how the P and N junctions are arranged in a PN junction. P region and the N region. So, this is going to be P and N. So, this is how we denote that. P and N semiconductors inside a junction diode is illustrated in figure A. This is figure A. So, P and N regions. Is that clear? And the symbol used for a diode is shown in figure B. So, here if I have figure B, I will show you all the symbol used. This is the symbol used for a diode. So, here it is the figure B, that is the symbol of a diode. Symbol of a junction diode. Or a PN junction diode. Now, here you can see this triangle, it looks like an arrowhead. So, from that you can identify that current flows in this direction. Always from P to N, across the PN junction, from the P side to the N region. The same way, this line represents the P region and this point represents the N region. So, therefore, you can understand that the current flows in this direction. This side is P, this side is N. Is that clear? So, this is figure A, figure B, and there is a figure C. Terminal A is known as the anode and terminal K is known as the cathode. This is something you all have to know. Terminal A is known as the anode and terminal K is known as the cathode. Now, in this particular diode, now I will draw that as figure C. Figure C. So, here this is anode and this is cathode and this is the positive terminal. I will put it on top. This is the positive terminal. This is the negative terminal. And this terminal is known as the anode. That terminal is the cathode. But we use the letter K to mark cathode. Anode is denoted by capital A. Cathode is denoted by capital K. And here also you can see the direction. I will use a different color. We can show the direction of the current flow that way. Current flows in this direction. From positive to negative terminals or anode to cathode through the junction diode. So that is something you have to remember. Electricity is conducted through the junction only when the anode A is connected to the positive terminal of an external voltage supply, and the direction of current through the junction is shown with an arrowhead in figure C. So I have shown that to you all already. That is how you use the diode. So if we consider the connection, now these are the symbols. So here so this is the P region, N region, positive terminal, negative terminal. When positive is connected to P and negative terminal is connected to the N region, current flows through the PN junction. So this is a forward biased circuit. The same way, if we use the circuit symbol, then you will see so this is positive, negative, current flows through the diode, PN junction diode. And this is the anode, this is the cathode or the positive terminal, negative terminal. And that is the direction of the current flow. Current flows in this direction. Is that clear? So this is how the PN junction, the P region and the N region are present in a diode that is shown here. And this is the circuit symbol. So you have to remember that. You can remember this line like as if it prevents the flow of current. So current cannot come this way. Whereas the arrowhead or the triangle shape shows the direction of the current flow. So that is the circuit symbol, and this is how you draw a circuit when the diode is forward biased. Is that clear, students? So then we will move on to the next slide. Here you can see in this diagram we have a diode. This is the outward appearance. Now here you can see there are two terminals. This is like a cylindrical structure, and on this side there is a silver color or white color line, and here you can see the writing there. I told you all they are referred to by serial numbers. So that is what is written here. And A denotes the anode, K denotes the cathode. So when you look at a diode like this, that looks like a cylinder with a line on one side of the cylinder. The side that has the silver or white line is connected to the cathode terminal, that is the negative terminal, and the other terminal will be the positive terminal. So here this is going to be the negative terminal and that is going to be the positive terminal. So this has to be connected to the positive terminal of the power supply, that has to be connected to the negative terminal of the power supply, and the current will flow in this direction. current will flow in that direction. So if we look at the explanation given there, the general outward appearance of a junction diode is shown in figure. It has a cylindrical shape and a black color. The white or silver colored ring shows the terminal of the cathode. There are a large number of different types of diodes and a number is printed on the cylinder in order to identify them. But it should be remembered that the external appearance of a diode can vary widely. So this is the appearance of a common diode that we use in the lab. But the appearance can vary. You all have to keep that in mind. So now that we have discussed the appearance of a diode, let's go to the lab and have a look at a diode now. Okay, students. So as I told you all, we will have a look at a diode. So this is a PN junction diode. You are familiar with this. Now the P side has holes and the N side has more electrons. Those are the charge carriers, and that is how the PN junction diode conducts electricity. So if you look at a diode, this is the physical appearance of a diode. Now here you can see this part is the diode here. And you can see the two terminals there. Now, if you look at this side closely, you will see a silver color or white color line. Can you all see that? This side. Right. So, that is the cathode or the N terminal. Now, if I hold it for you all to understand more clearly, I have a diagram here. You all know we can use different symbols for diodes. Now, this is one symbol where the P and N junctions are denoted there. This is same as the second symbol where we have a triangle that shows the direction, or we can take it as an arrowhead that shows the direction of the current flow. So, in this, if we hold the arrow like this, you can see this is the P terminal, this is the N terminal. So, current flows from this towards the N. So, current flows in this direction, from this terminal P towards the N terminal there. Or else, if you take this symbol, here you can see the direction of the current flow from here to here. So, in this, where you have the silver line, like I told you all, that terminal, this terminal is known as the cathode. This terminal is the cathode. And this terminal is the anode. P terminal or anode, and this side we have the N terminal or the cathode. Always current flows from anode to cathode or P to N. So, when we use a diode, as we have already discussed, students, when we connect a diode, we always connect the P terminal to the positive terminal of the battery and the N terminal or the cathode to the negative terminal of the battery. So, that is how we use a PN junction diode. I'm sure you all can understand that. So, always look at the diode, look for the silver color band. If it is a diode like this, a PN junction diode, you have to look for the silver color or the white color band. From that, you identify the terminals. So, that is how we use a PN junction diode. So, students, you all saw the diode in the lab. So, you all know how to identify this white color or silver color line, and then you can identify the terminals and how you are supposed to connect the diode. So, with that, students, I will move on to the next slide. So, here we look at a function of a diode, that is rectification of alternating currents. That is the first function or one of the functions of the diode that we are going to discuss. Now, are you all familiar with alternating currents and direct currents? I am sure you are, because we have discussed this when we discussed the lesson Household Electric Circuits. The electricity that is supplied to the household. You can remember it has a potential difference of 230 volts. The maximum current that can flow into the household is about 40 amperes, and it is an alternating current, AC current, with a frequency of 50 Hz. So when we say alternating current, the direction of the current changes with time. So once it flows in the clockwise direction, then the direction changes to anti-clockwise. Like that, if the frequency is 50 Hz, the direction will change 50 times in a second. So that is an alternating current. Now the current that is generated by the dynamo, it is an alternating current. But the thing is, the devices that we use in the household, most of these devices, they need a direct current. Direct current means the direction of the current does not change with time. The current flows only in one direction. For example, the current generated by a battery, that is a direct current. So, if we use direct current appliances in the household, we need to convert the alternating current to direct current. So, that can be done using a diode, and that process is known as rectification of alternating currents. We know that an alternating current is a current that alternates or changes its direction of flow in a circuit. So that is something you have to remember. Alternating current is a current that alternates or changes its direction of flow in a circuit. And a direct current is a current that flows only in one direction. The variation of the current or the voltage with time for direct currents and alternating currents are shown in figure. So, if we try to look at the change in voltage or current, now I will draw the two graphical representation of alternating and direct currents here. So, the first one is going to be alternating current. The second one is going to be direct current. So, we will draw that now. So, here we will have the axis, that is the y-axis. I will draw both the axes here. Then we will have the x-axis, that also here. So, here the y-axis can be voltage or current, and x-axis will be time. And here also this can be voltage or current, and that is going to be time. So, if we plot the voltage or current, you all know it will vary, the direction will change. So, here what I will do is, I will mark the positive and negative potential, if that is going to be the same one. So, here this will be positive, this will be negative, this is the 0, 1. So, here if we look at the variation in potential, it is going to be something like that. So, here you can see it is positive potential. Here it is negative potential, again there it is a positive potential. So, the potential or the current will vary with time. You will get the positive and the negative potentials, or the current in the positive direction and the negative direction. That is an alternating current. So, with time. Here you can see, another thing you can see here is that, here you can see students, there is a point where this changes, and between these two there is no positive current, and at that point the potential or the current becomes 0. Here also it is 0. Then there is a maximum value and a minimum value. Is that clear, student? So that is how an alternating current is. It changes with time. The potential or voltage or the current changes with time. But if we take the direct current, now the direct current, there is no change. With time, it is parallel to the x-axis. There is no change in the voltage or current. The direction does not change. So if it is a direct current, it will be either in the positive direction or in the negative direction. This particular graph, the line will not cross the 0 point or it will not cross the x-axis. Here you can see it crosses the x-axis. But here the current or the potential difference will not cross the x-axis. It will be only in one direction. That is a direct current. So this is an alternating current. That is a direct current. I am sure you all can understand that. So like I told you all, the dynamo produces an alternating current. But there are some devices that need direct current. So this alternating current has to be converted to direct current. For that, what we do is we use a diode. Now what is the function of a diode? Now you all can remember. Diode allows the current to flow only in one direction. That is the forward biasing direction. Current will flow only if the P region of the diode is connected to the positive terminal and the N region is connected to the negative terminal. That is the forward biasing. So what will happen? Now when we have a diode connected this way, a diode connected like that, it will allow the current, or I will say, so here it will allow the current to flow this way. But current cannot flow in this direction. It is not possible. So if it is an alternating current and if we connect the diode, when the direction of the current is this way, it will allow the current to flow. But when the direction of the current changes, it will not allow the current to flow. So there will be regions, there will be time frames when the current flows through the diode, and there will be time frames where the current does not flow through the diode. So that is the basic concept of rectification. We use a diode and make the current to flow only in one direction. Now we will try to understand how we can do that. So with that, I will move on to the next slide. So here you can see, usually dynamos produce electricity as alternating currents. So what I told you, dynamos produce electricity as alternating currents. However, for operating some electronic devices, direct currents are required. Junction diodes that allow the current to flow in one direction can be used for converting an alternating current to a direct current. So, for converting an alternating current to a direct current. And this is the definition or the explanation as to what rectification is. You have to remember that, students. The task of converting an alternating current into a direct current that flows only in one direction is known as rectification. So we will be doing this rectification using the diodes. That is important. So then I'll move on to the next slide. So first we will look at half-wave rectification. I will explain that to you all. Now I told you when we use one diode, it allows current to flow only in one direction. Because of that, it doesn't allow the current flowing in the opposite direction to flow through it. So only half of the current, half of the wave that I drew earlier will flow through the diode. That is why we call it the half-wave rectification. Now we will look at this diagram. Figure below shows a circuit used for half-wave rectification. The main power supply is used to obtain the alternating current. So you all know the household, the main power supply is alternating current. I told you all that. Here you can see it has a potential difference of 230 volt. It is an alternating current with a frequency of 50 Hertz. So this is what I told you all before also. What we get from the national power supply to the household. From the power supply grid, the national grid to the households. So that is taken here. Then look at this symbol. That is a step-down transformer. Now the step-down transformer converts this 230 volt current to a 3 volt alternating current. It does not change the nature of current. It is alternating current. Only thing it does is decreases the potential difference. When we say step-down transformer, it decreases the potential difference. So here we can say step-down transformer decreases the voltage of the alternate current supplied to it. So here the purpose of using step down. You will be discussing transformers in the coming lessons for y'all. When I discuss electromagnetism with y'all, I will discuss the function of transformers. So here step down. So that means reducing, stepping down. So the potential difference decreases. So from 230 volt alternating current, the current becomes 3 volt alternating current. The frequency doesn't change, it is still 50 Hertz, and the nature of current also does not change. Only the potential difference changes. Is that clear? So this is 230 volt becoming 3 volt alternating current. So then, now this 3 volts is enough to forward bias the diode. You all can remember we used a 3 volt battery in the previous one also. So here what happens? Now you have the step down transformer. Then we have point X and point Y. Now there is the diode here. Now in this diode you all know the direction of the current flow. That is the direction of the current flow. So alternating current, when current flows through X, the diode will allow the current to flow. So current comes this way. Now this is point L and that is point M. In between there is a resistance R. And here you can see this arrow indicates the direction of the current. So the current that is coming out of the step down transformer will come to the point X, flow through the diode D, then to point L, through the resistor, and then to point M, to X, and back to the circuit. So that direction current will flow. But the direction will change now. alternating current. So then what will happen? Current has to come this way, come to point Y, then to here, go this way. But when it comes to this point, will the diode allow the current to flow? No, because it will be reverse biased. Therefore, current cannot flow in this direction. So, only the current that flows from X through the diode will flow. The other part of the current will not flow. So, therefore, we will get a graph like this. Current through R. Only the positive current will flow with time, but where the negative current should be, there is no current flow. Is that clear to you all? So, if we look at this component only, I am not going to draw this step down transformer and all that. I am going to only draw this part of the circuit. So, here you will see, students, here you can remember the graph for the alternating current. So, it was something like this. What I will do is, I will change the color of this. I will make it blue color just for us to understand what happens during rectification. Then we have the rectifier circuit. So, we have the rectifier circuit. Here we have the diode. So, here we need to have the diode. Then, okay. So, this is point X. This is point Y. So, initially we will take this as the positive current. So, what will happen? The positive current will flow this way. Through the diode, it will come. Then we have the R, the resistance. And then we have point M. This is point M, and to point Y. The current will flow. Now, although this circuit looks incomplete, you all know this part is there. We have the power supply, step down transformer. So, here the current will flow. So, then if we draw the graph for the rectified current, again you will have the y-axis, then we have the axis here. So, this is voltage, time. You all know it can be voltage or current. So, here also this is voltage or current. Now, here the positive current flows. This is one direction through X. So, that current flows. But when it is this region, now this region, the current cannot flow. This way, current cannot flow. Now, this is not possible. Now, even if the current comes this way through the resistor, but at this point, the diode will be reverse biased. So, because of that, that current cannot flow. Then again, the direction will change to X, then through the diode, it will flow. So, that is how you will get the next part of the graph. So, first this one, Then let's say this is 2, this is 3. So 1 is here, the second half is not there. Again you will get the third half. So that is how the rectification will take place. This part of the graph will not be there. It will not flow through the circuit. Is that clear? So this is half wave rectification. Why? Part of the curve. Now this is a full wave, 1 and 2 together is one full wave. But out of that, only one is there. Half of the wave is there. That is half the wave that shows the current is there. So that is why we say half wave rectification. Diode allows the current to flow only in one direction. So therefore, it is going to be half wave rectification. The second half of the wave, that is in the opposite direction, will not flow through the PN junction diode. Is that clear, student? So this is something that you all have to understand. Rectification of alternating current to convert it to direct current. If we use one diode, it will be half wave rectification. So with that, I will move on to the next slide. So here, you can see first the voltage is lowered to a desired value using the step down transformer. So the voltage is lowered using the desired value using the step down transformer. The lowered alternating potential difference is obtained from the XY terminals of the transformer. Since the current flow through the diode takes place only in the direction XL, the current through the resistance R flows only during the positive half cycle of the alternating current. That is what I explained to you. Current through the resistant R flows only during the positive half cycle of the alternating current. During the negative half cycle, the current through the resistance is 0. Compare this with the way the diode behaved when the batteries were connected in activity. Earlier when we tried to understand the biasing of the diode, that is PN junction, this is how it behaved. Since the output always consists only of half a cycle of the current, this is known as half wave rectification. Half a cycle of the current, and that is why we call it the half wave rectification. Now to explain this part, to compare it with the way the diode behaved when the batteries were connected in the activity, I will show you all that diagram. So here we connected it in two ways. So here we have the diodes there, positive and negative terminals. Here also I have the diode, positive and negative terminals. Then we have the resistors. So that is the resistor R. Here also the resistor R. Now consider the alternating current. Now the alternating current, how is it? We have the positive and the negative cycles. Now here of course I will use different colors. We'll take this as the positive current. and this is the negative current. So positive current we will take as going through X. So this has to be the positive terminal and that will be the negative terminal. Positive, negative. So here this is going to be point Y. So current will go this way, it will flow through the diode and it will come through the resistance. There the current will flow. So when you get the current flow, what happens there? You will have the positive cycle. But when we connect it the other way, where you have the negative terminal here, positive terminal there, then how does the current flow? This way, this way, this way, that way. But that is not possible. So there the current flow is not possible. Current cannot flow this way. This is not possible. So because of that, you will not get that curve here. So this is the forward biased instance. This is the reverse biased instance. Is that clear? So this is reverse biasing, reverse bias, and this one is the forward bias. So here of course we have the current with time on this side, time, here also current. So from there to here, alternate current becomes direct current. AC is alternate current, DC is direct current. But here what happens is only half wave rectification. Only half wave rectification. Is that clear? So this is how you compare it with the forward and reverse biasing. Here you can see, compare this with the way the diode behaved when the batteries were connected in the activity. So this is how we connected the batteries. No? First we connected the positive terminal with the anode of the diode. Then we connected the negative terminal with the anode of the diode. So this is forward bias, allows the current to flow through it, the pink color arrows, whereas when you change the terminals, that is like the negative current. But that current, that is reverse bias. Here it has to be reverse bias. This should be reverse bias. Reverse bias. So when it is reverse bias, the current does not flow. Is that clear to all students? So this is how we can compare the half wave rectification with the biasing of the PN junction or the PN junction diode. Since the junction diode is used for rectification of current, we also call it as the rectifier diode, because it is used to rectify alternate current to direct current. Is that clear, students? So then I will move on to the next slide. So here exercise 11.1, plot the current obtained through R when only the terminals of the diode in figure 11.13 are changed so that X is connected to the cathode while all the other parts of the circuit remain intact. So here what they want you to do is, they want you to alter the circuit. Instead of changing the terminals, they want you to change this part. Now here you can see this side is anode, this side is cathode. But there they want you to draw the circuit when the X is connected to the cathode. So the diode has to change. So we need to redraw this diagram and we need to observe the graph. So if we do that, now here we need to have this component, then here the diode, so here we will have the transformer, so here we are going to have the diode. The diode has to be in the opposite manner. It has to be connected this way. And we have the resistor there. Then here, of course, we have the transformer. So this is a step-down transformer. This is the symbol. You have the coil, input coil, output coil and two lines to indicate the step-down transformer. So here we have the points where we supply 230 volt, 50 hertz alternating current. But here it becomes 3 volt, 50 hertz alternating current. And these points, this is point X and this is point Y. So that is how they wanted us to connect it. This is the cathode, this is the anode and this is R. Now how will the current flow? If we plot the graph, so it is going to be the graph here. So you will have the graph there. Now when the current is like this, the diode is here, the current can only flow in this direction, that is this direction. So when current comes to point Y, it can flow through the resistor, through the diode and come back. So here you can see when the current flows this way, you have the positive currents only. Positive half cycles of the current flow. Now the current is flowing in the opposite direction. Then what will you have? You will only have the negative half cycles. So here we will only have the graph like that. If we extend this line, if I extend this line, you will see this is the current and this is time. So only the negative half cycles will be obtained there. No positive half cycles. Can you all understand that? So the same circuit, only difference is the way the diode is connected varies. So in this first one, we have the diode where X is connected to anode and Y is connected towards the cathode. So their current flows in this direction. So that is the positive half cycle of the current. So you get only the positive half cycles. But when we change the direction of the diode, where the cathode is connected to X, current flows in through Y, therefore current flows this way. When the current comes through X, the diode does not allow the current to flow. So you will get a graph like this, where you have only the negative half cycles of the current. Both represent half-wave rectification. Both are half-wave rectification, not full-wave rectification. Is that clear? So, this is what we discussed before. This is what we were supposed to do. So that X is connected to the cathode while all other parts of the circuit remain intact. So the rest of the circuit is the same. Only thing the diode has changed. Is that clear, students? So I am sure you all can understand that. So then, with this in mind, now that you all have understood what half-wave rectification is, but you all can understand this is not enough for an electronic device to function. For an electronic device to function, you need to supply current continuously. Now here the current flow is not continuous. Only half of the wave flows through the device. Same here also. So then we have to have a way of converting the alternating current completely to direct current. And that process is known as full wave rectification. So I will end this chapter here, and in the next chapter I will discuss the full wave rectification with you all.
To watch these important lessons, subscribe to DP Education's YouTube channel right now. Click on the bell icon to stay updated on the latest lessons. Sri Lanka's largest free online school, DP Education.